So the next talk will be from Phil Young, and the title is Current Sorry State of C11 Code and a Suggestion to Fix It. So it's mostly about using C11 atomics, which the compiler can use to have some more generic code in the DPDK, so we can have good performances on any processors.
Okay, good morning. Phil Young made this proposal, and I, together with him, make this slide. Currently, he has some problems with his neck, so he can't attend this event. So I will help present. So today I will talk about how RT atomic APIs within DPDK are implemented for different architectures, for x86, for PowerPC 64, and for ARM64. And what are the problems, and how to fix these problems. And at last, I will talk about how ARM64 are evolving from the microarchitecture instructions never to better support C11 atomic APIs. So how does the RT atomic family APIs look like? It provides such kinds of APIs. It marks up the difference of different architectures. So it provides all common APIs for the libraries and for the applications. So you don't need to care about the difference below the underneath, the different architecture details. The goal is good, but let's see what's the problem with these APIs. Okay, this is the implementation on x86. It's based on lock prefix, and lock prefix instructions has a strict memory order, and the loads and stores will not be reordered across these locked instructions. So when you call this API on x86, the order is kept. It will not be reordered with other loads and stores. So this is the implementation on PPC 64. Part of the APIs, it kept the order. You can see in the beginning, it have LW sync, and in the ending, it has async instructions. So this API, compare and set, the order is ensured, it's guaranteed. But for this API, atomic add, you know, PowerPC is a relaxed ordering model. So the load and stores can come across this atomic API. Then let's see how these APIs are implemented on ARM64. Currently, we have generic implementation. For ARM64, we are using the generic one. The generic implementation is based on, it's implemented with the GCC sync built-ins. Later on, we will look at what the problems with the sync built-ins. Maybe you know sync built-in is in deprecation. It should be replaced by atomic built-ins. Okay, I made a summary about these different architectures, have different implicit ordering semantics. For as I just talked about on x86, the loader store come across the APIs. For PowerPC, some of the APIs come across, and the other APIs can cross. On ARM64, later on I will show the disassembled code. we have, in the end, we have a DMB. This DMB is a full barrier. So in the bottom, the load and stores can't across. But in the top, the load and store can cross. So on ARM64 is like the bottom line order is kept, but the top line is not. So in one word, the atomic APIs, in terms of the AutoMeCity, it's OK. These atomic operations can't be interrupted by other load and store accesses. But in terms of ordering, memory ordering, it has a different implicit ordering. So that make this inconsistency by definition will cause some problems. I will talk about what kinds of problems it will cause. The first one is flexibility. So by definition, these APIs didn't take any arguments about memory ordering. So as I just showed, different architectures made the implementation with different memory ordering semantics. Fixed. So within which implementation, the ordering is fixed. For x86, it is very strong. For ARM, maybe partial strong, but maybe for some use cases, it's strong enough, but it hurt performance. But for some other use cases, it's not strong enough. So these APIs have fixed memory ordering semantics for each implementation, no flexibility. The second problem is inconsistency. So each platform has its own memory ordering semantics, and they are not synced, aligned with each other. And so the third problem is performance. As I just talked about, maybe too strong memory ordering is not suitable for some use cases. It will hurt performance, especially for weak memory ordering platforms like ARM64. And for correctness, the last one is the correctness. If the use cases requires stronger than actually provided ordering semantics, then something will go, some synchronization will go wrong. So how can we fix this issue? So we propose to stop using these RT atomic APIs, and we already have C11 atomic built-ins. So for the new code, we can use these C11 atomic built-ins. It offers different memory ordering semantics like relaxed, acquire, release, and consistent sequential. This kind of, you can freely select which ordering you want. For the missing APIs, this language doesn't provide, like maybe 128-bit compare and exchange. We can provide new APIs. This patch is for 128-bit compare and exchange atomic API for ARM platforms. x86 has also such kind of patch merged. So why do we need this relaxed, do we need this ordering semantics? You know, ARM64 is known as a weak memory ordering. So it can, the CPU or the compiler can make full use of this weak memory ordering out of order execution for performance tuning, for performance improvement. So C11 has provided this kind of semantics. Like for example, for relaxed mode, the first one, you can reorder load and store, and in two ways. For acquire, you can reorder the old load and stores to the younger side, and vice versa. It doesn't allow. And for release, it can be reordered in the other way. So you can freely choose which ordering you can use to make full use of this out of order execution to help for performance. This is the one API example on ARM64. You can see currently this kind of sync built-in based implementation. In the end, it has one full barrier. This one full barrier, two-way barrier, is not necessary. It hurts performance. And even for the store release, this release order, sometimes it is required for some use cases. But for other use cases, it can, for example, if it was used for statistics, it is not necessary. It can be removed. So C11 Atomic APIs provide such flexibility. Yeah, the left side is implemented with sync built-in. The right side is implemented with atomic built-in, enforce the store release barrier. If I enforce maybe relaxed ordering, this store release this one-way barrier can be even replaced with no barrier. So this store this error can be removed. This instruction. We have implemented a lot of. We have used a lot of C11 atomic APIs to optimize for RT-RIN, for RT-stack, and for logs. You can easily find this code. So for new code, it is highly recommended to use atomic C11 atomic APIs. So let's talk about how ARM64 is evolving to better support C11 atomics. V8.0, we have introduced the load acquire exclusive register instructions and the store release exclusive register instruction. You can see for load acquire, the following read and write. The following load and store can't be reordered across above. And for store release, it can't be reordered after that. This kind of one-way reordering is very useful for use cases like producers and consumers. For on V8.1, we introduced LSE atomic instructions. In the previous slides, to implement atomic, oh, not this one. Let me check. Okay, for V8.0, if we want to implement AutoMeCity, we have to here use load exclusive and store exclusive. If store exclusive means if during this period, load and store, during this period, someone cut in and break the AutoMeCity. It have to retry the loop, retry again. This is a loop. With these new instructions, the loop can be removed because the new instruction can guarantee the AutoMeCity. This is about V8.3. We introduced the load APR instruction. This one is as I show. So the previous load acquire and store needs, even this store needs store. I don't know. Do I have a laser? It can't be. You can reorder. You can't reorder here. And this one with new instructions, the following load acquire instructions can be reordered above. This provide more relaxed. It's more relaxed, so it can be beneficial to performance. So what's the key takeaways? As the first one, I talked about the current RT atomic APIs, what's the problems. Second, I recommended the C11 atomic APIs are more flexible and more relaxed, offered more opportunity for performance tuning. And in the third part, I talked about how ARM64 new instructions better support C11 atomic APIs to be more helpful for performance. That's it. Thanks. Any questions?
I've got one question that could be partially to you, partially to packaging and distribution guys. Hello, okay. I'm here.
Okay.
I'm waving a hand to you.
Okay.
Okay, you cannot see because of the lights. Yeah. So, since our ARMv8 has actually 3 generations of atomic instructions, some projects actually, did quite a lot of work to make sure that to ensure binary compatibility. Because right now, in order to take full advantage of remote atomics, you need to compile the code with the architecture switch that says this is ARMv8.2, not the ARMv8.0. So default ARMv8 compiling mode would not use these instructions, right?
Yes.
So the question is, what is the route that packaging guys and people that would like to provide binary distributions, what is their policy? Because on generic ARMv8 platform, you don't know which version is it, and then you need to use default instructions which are from ARMv8.0. So Linux kernel, they did a special mechanism to make sure that they stay binary compatible, but they can switch the implementation. But this is kind of over-engineering, I think, for DPDK, right? To patch the code, to use live code patching in order to switch the atomic mode. So I'm not sure if this is a question to you, but what do you think? What would be the default compilation mode for binary releases?
Okay, this is a kind of deployment issue, right? So I don't know how to fix this. So maybe it's up to the VM or Ubuntu to how to release this. The binary can be compiled for different architectures. You can indicate V8.0 and V8.1. But the final binary is different, right?
Yeah. As long as somebody is using the source code and compiles itself, everything is fine. But if somebody would like to use a Debian or Fedora package, then there's an open question: what kind of architecture is going to be there?
Gavin, can I answer this question,
if
you don't mind?
Thank you.
So I think that's a very valid question. right? How do we how do we use the most efficient atomic instructions at runtime? So right now, we are trying to solve it through the compiler. So if you use the C11 atomic APIs, the compiler will emit this code, which will basically check the capability. So it's a if v8 dot something else, use these instructions, otherwise use the 8.0 instructions. So we have tested that patch in the DPDK context, and it's a slight overhead. It's an overhead of around 1.4%. And again, it differs from platform to platform, but it's a slight overhead, and we think that that should be good enough, because if we are looking at other alternate solutions, as you said, it's over-engineering. So, yeah. So I had one quick comment, Gavin. I think the point that we have to emphasize is by using the C11 atomic APIs instead of RTE atomic APIs, we don't see any performance degradation on x86 platform. That's what we see in our tests, right?
Last question.
Hi again. A few years ago, there was a patch from Adrian to update our headers to make compatible them with C99. So, C99. We didn't explicitly say it, but it implies that DPDK is supported by C99 compilers or applications built for that one. Should we explicitly say now that we support C11 in DPDK? Because will they able to compile, if any old application supports C99, will it able to use and compile with these headers?
Yes, I noticed there one component. It's called failsafe. It has
Yes,
forcibly
it explicitly says gives the parameter for C99.
yes.
But also, as I said, all headers was made compatible with C99. So perhaps it can be good to explicitly say we now support C11.
Yes, I think
don't know if
I think
any
it's the right
objection
time
there.
to use C11. I ever tried to I see the failsafe forced C99 because it has got some compiling issues with very old GCC version.
4.7.
Yeah,
I just checked.
4.8, GCC 4.8. So if we maybe, I see in DPDK at least 4 dot line is recommended, right? At least 4 dot line. So I think
As a compiler can be, but I think it can be good to start a discussion and explicitly clarify we support this or that. I think better to clarify it.
yes, yes. Maybe we can even, there are some at least in RT-Rin we have different versions. One is for 11 and one is for generic. So maybe in the future we can totally remove the generic one and to decrease the duplication and enforce the C11 version. Questions? Thank you. Further.
Yeah. Actually, I think the Atomic is partially implemented in the compiler, and a big part of it is in the libc, is in the libraries. So, what is the status of the library support for C11 Atomics?
You mean this atomic APIs?
Yes.
Is, where it comes from?
No. Since when does glibc support the C11 Atomics library?
Yes, I think it's quite a long ago. C11
Yes,
was
C11,
introduced.
But I think, for example, I know that the C11 Swed libraries have been added like 1 year ago or something like this to glibc. So, since when does C libraries support Atomics?
Was supported for a long time. Yeah, at least for C4.9. Since 4.9, it was supported. Yes, yes.
Okay, but I think the C11 atomics are half of the functionality are in the compiler, and the other half is in the C library, libc.
If the instructions are natively supported, then it's the compiler directly emits those instructions.
Yeah, but it's not the exact C11 function. I mean, you might have to. Well, it won't be the C11 API. I think.
Maybe I'm not understanding the question, but what I'm trying to say is that the library comes into picture only if the underlying architecture does not support the atomic instructions natively. So, for example, if you take 128-bit atomic APIs, at that point, it differs to the library. Library implements its own methods to guarantee 128-bit.
Okay, thank you.
If it answered your question.
Yes.
Okay, thank you. Any more questions before? Okay. Thank you.
Do we have a next speaker?